Hey guys, so excited. Today we're going to talk about dot products. Now, when I was in school taking linear algebra, what they told us dot products were basically is the dot product U dot with V equals U1 V1 plus U2 V2, which it ends up being a scalar. All right. The problem with this is that we never got an understanding of what in the world these things are. And so that's what I want to do today is explain what the dot product is, what it does, how it's helpful, useful. It has one main purpose. Its main purpose is to determine whether or not two vectors are orthogonal. So the dot product helps determine if two vectors are orthogonal. Orthogonal is just this fancy term, just means perpendicular. And the beautiful thing about it is whether you have vectors that are in 2 dimensions or 3 dimensions, you can determine whether they are orthogonal with this dot product test. Now, how does it work? Why does it work? I'm going to explain in this simple little proof. All right, so the first thing we're going to do is let's just take two vectors that are orthogonal. And we can think about them kind of in the Cartesian coordinate system. Let's just do it in 2 dimensions for now. And let's say I have my vector u right here, okay? And I've got my vector v that is a 90-degree angle with u, okay? And let's call this vector that connects them, we'll call this vector capital U V, okay? We'll call the vector that connects the two capital U V, all right? Now, there are a few things that we can say about U V here. We can definitely say that the magnitude of UV, this looks like a U, squared equals the magnitude of U squared plus the magnitude of V squared. Now, why can we say that? Well, straight up Pythagorean theorem, right? UV obviously is the hypotenuse here. So A squared plus B squared equals C squared. Boom, we're done. All right. So the next thing, but let's think about it in terms of its components, right? If we think about it, we can say this point right here is really U1, U2. U1, of course, being the X value, U2 being the Y value. This point down here is V1, V2, right? V1 being the X value, V2 being the Y value. All right. Now, all that said, let's think about what we could characterize UV as. Well, think about it. The distance between this point, U1, U2, and this point, UV1, V2, we could just use the distance formula, right? And remember, the distance formula is a square root of x2 minus x1 squared plus y2 minus y1 squared. So let's just look at it in terms of its distance, right? So we could say the magnitude of UV, in other words, the length of this right here is just the distance between this point and this point down here. So what's the X values of my point? Well, U1, V1. Let's say that V1 is our X2 or something. So we can say this will be V1 minus U1 squared plus v2 minus u2 squared. All right. Well, let's say I decided to square both sides. Well, that would give me the magnitude of uv squared equals v1 minus u1 squared plus v2 minus u2 squared. Okay, well, what if I square both of these here? Okay, if I FOIL it out, that gives me v squared equals v1 squared minus 2v1 u1 plus u1 squared plus v2 squared minus 2v2 u2 plus u2 squared. All right, and that's just FOILing it out, right? Then let's regroup it so the u's, the v's, and the 2's are all together. So I have it like this. Looks kind of like something like v1 squared plus v2 squared. And I'm going to kind of break this up because I want to show like what different things are different. So let me grab another marker here. So that's u1 squared, here we go. And then we're going to have plus u1 squared plus u2 squared, okay, minus 2 and then I'm going to try to get it in there, but it's going to be kind of tough, but I think we can get it. So we got this v1u1 and we got this minus, we got this, I guess it would be plus v2u2. Okay, ooh, we got that mark on there. All right, boom. So that said, well, this should look really familiar. v1 squared plus u1 squared, because that's what the magnitude of v is. I mean, think about it. Magnitude of v squared, we have it. Magnitude of v squared is just your components. v1 squared plus v2 squared. And the magnitude of u squared is just u1 squared plus u2 squared. So what I could do is I could just take these and replace it with the magnitude of v squared and the magnitude of u squared. What? Okay, let's do that. So that gives us the magnitude of uv squared equals the magnitude of v squared plus the magnitude of u squared minus all this junk back here. Now comes the fun part. Notice, we already had by Pythagorean theorem that uv squared plus u squared plus v squared, all this junk up here was already just u plus v. So let's take this and replace it with this up here. So then we can say the magnitude of u squared plus the magnitude of v squared equals magnitude of v squared plus the magnitude of u squared minus 2 v1 u1 plus v2 u2. But we're not done yet. What if I subtracted the magnitude of u and v squared on both sides? Well, that will leave me with 0 equals negative 2 v1 u1 plus v2 u2. And therefore, if I divide by -2 on both sides, I get 0 equals v1 u1 plus v2 u2. Which, if you remember, this is the dot product. So that brings us to our theorem. If vector u and vector v are orthogonal, then u1 v1 plus u2 v2 equals. And this right here, of course, is we could say the dot product is 0. All right, I hope you guys enjoyed that video. That was it. That's the main idea of the dot product. On the next video, we're going to do some problems with this. But the main thing is, if you have two vectors u and v that are orthogonal, they are perpendicular, then their dot product is 0. Don't forget to like, subscribe, do all of the things, hit the notification bell, and I'll see you guys in the next video.